All right, so welcome to M5, and welcome to the third talk in our series of Departmental Honors Senior Thesis Talks. Today we're very happy to have Michael McKinley here, and he's got all kinds of great things to explain. And let's see, as far as upcoming events, next Tuesday, Alex is back. Alex Trafonis will be back explaining Facebook application. So he and his team in the SDP have created a Facebook application using the Facebook API, and he's going to take that apart and show how one would create one's own Facebook application. All right, Michael, thank you.
Thank you.
Welcome.
So I'm Michael McKinley. I'm a graduating senior ComCall student in the Mechanical Engineering Department. And I think after last week I was, the example set forth to bring your own posse was a good choice. So I tried to do that myself, but unfortunately I don't think most of them got past the EE bouncers at the door. So anyway, today I'll be talking about how we use some interesting properties of polymers to create text on extruded plastic. So as is shown by the title here, that's let's see. Oh, come on. Get some issues with the mouse going on here. All right. So, kind of the basis of my project is the production of shark skin. Shark skin is a micro ridge-like structure produced on an extruded surface. And this comes about as a result of an instability that occurs at the exit plane of a die. So you can see here in this diagram, we've got a bulk flow of plastic in this region. It's being extruded through a die face, and due to a temperature gradient, the die exit plane being a lower temperature than the bulk flow, we get a stress singularity. And so this happens as a result of a no-slip boundary and the bulk extrudate rapidly accelerating to the plug flow of our polymer. So as a result, if this temperature gradient is too high, we get some pretty severe ridge-like structures, as shown in this image here. And these can be, up to about 100 micrometers in scale. In industry, this is a big problem. So you don't want your extruded plastic to have a surface texture like this. But we're actually using this to our advantage to produce some interesting textures. So a little bit of background. This project came about 5 years ago, I believe, by a student named Eric Miller, who was getting his master's degree over in mechanical engineering. He was working on a single gradient shark skin project. And so basically we have here is a schematic of his die. So we're able to produce a temperature gradient between the main heating zone of our extruder and that output plane of our die. And in doing so, we can create a single extrudate difference in shark skin in one dimension. So we can see here we got cylindrical shark skin of varying degrees, and the difference in shark skin magnitude is created by difference in temperature gradient between your bulk flow and your output plane. So moving forward, the next step is to say, well, okay, we can do that in one dimension. How about two? So we got two different gradients going on here on either side of a square die, this stainless steel looking chunk. And where you've got two heaters, two different heating implements, and it's the same technique more or less. So I'm expanding further and saying, well, how small can we actually get this, and how tight can we pack these features on a single extrudate plane? So we got some images here of my design. It's a similar interfaces with the same extruder barrel as before, so I don't have to deal with that problem. But we're looking at a die with three heater pins, and each heater pin is a temperature-controlled loop. And we'll talk more about that later. But you can see here so these are brass heater pins separated by an insulator layer, and in a main heater block, which we can maintain as a temperature. So if you look at this drawing here, we can see as this extrudate is coming out, the last surface in contact is this temperature-controlled pin. And so right in these regions, we can control that surface texture and hopefully create some interesting designs, well in this case letters is our proof of concept. So here's an image of the extruder itself. We've got a main temperature controlled barrel. So this is aluminum obviously, and we've got heater bands in 3 places. And that's used, controlled by an industrial heater controller. And then we've got, so that's kept at around, say, 150 C. We've got high pressure line nitrogen tank behind here. You can see through this guy here. And that's rated for 2,000 PSI. So it's some interesting stuff. Here's our pellets that we have inside. Standard, it's more or less hot glue. It's run-of-the-mill plastic. And then here's another image of our extruder. So you can see if we get that cutaway. So our extruding surface is no longer in contact with our die as we're exiting our die head. And a final image here, we can see our heater pins and all the controls, the feedback part necessary to control our temperature. So we've got 30 gauge nichrome wire wrapped around our heater pins, and buried inside that head, we have some really small temperature sensors. This is a case, these are RTDs. I'm actually using LM35s, which are a temperature IC. So they're approximately the same scale. So I guess the LM35s are actually really nice because they interface with the Arduino without an issue at all. And that'll be part of my project later here. So you can see those pins are assembled and then epoxied in place. And our epoxy is our insulation barrier between each heater pin, each heater element. And one of the problems with the design is that you've got to actually machine these things in a specific order. So if you have a problem down the line, you've got to start over due to the limitations of our machining. So this design was pretty much pushing the limits of what we could do with the tools and techniques that we have available. So, I mean, obviously we're dealing with high pressures here, so safety's got to be our top concern, or at least top 3. Yeah, so I don't really think any of that would do me any good if it did let loose, but it felt better, and so we did. And the non-Newtonian Fluid Dynamics Lab actually looks at Kevlar as one of their projects. So they happen to have a Kevlar vest and helmet sitting around. It's like, well, I might as well put it to use. If something happened and I wasn't wearing that, that'd be a problem. So anyway, so it works. And that's the cool part. You can see here we get a pretty large difference in texture between our large surface ridges around the 100 micrometer scale here and our smooth surface here. And this is a coloration behind, so you can actually see the difference a little better. And that's just a kind of a gross start point with my design to see how well it was functioning. But then we get into the fun stuff. So we do an initial system identification on my die, so I could make a math model of it and simulate. So this is a regression-based system identification technique. Pretty simple stuff, and we fit first order, second order system to it, so I can get an accurate model later on. And then, obviously, we've got 3 heater pins. So if we want to print text, we need a specialized font. So this is my patented trademark 3-pin heater font. And you can download it from my website if you want to type your papers in it. It's a true type font. And, you know, naturally, if any of you got here late, we got start over again here. So we're in a comm call talk on Michael McKinley. It's legible, you know. And since this is, looks like Space Invaders, it's endorsed by Sun Ra, the spaceman himself, and his orchestra. 'Cause space is the place, right? So all fooling aside, we got to do some math here to make sure we know what's going on. So I did a 1.5 dimensional finite difference approximation for my temperature gradient throughout, and that's 1.5 in that it's we've got a 1-dimensional finite difference approximation, and then it's swept over an area just to get our idea of what's happening over time. Because all we really care about is that last interface with plastic. So the important things to note here is we've got our Fourier number, which is really the important part, and that's comprised of our thermal diffusivity of our insulation material. and obviously we got to keep stability criterion right, so we reach a convergence at the end. And so that can actually get some decent results here. So this is just to kind of show you graphically what we're looking at. We're modeling this interface right here with the heater pins as a one-dimensional heat transfer between a temperature-controlled pin, a temperature-controlled wall, and this insulated boundary layer. And so here's what our temperature would look like. So we've got actual data that I can take from my temperature sensors. That's from the heater pin. We've got a known constant temperature at the wall, and then a second order response from the insulation material. Well, it varies from first to second as you go through it. But anyway, so let's see here. Get a better picture of what's happening. So to create an M, we start with Albrecht Dührer's nice Roman uppercase M, and then we got my representation, which is 3 pixels of spaciness. And so we're looking at our M, and then we got some signals here that we're translating into heater changes in temperature, and my thermal approximation of what's happening in the surfaces around it. So the important thing to note here is that this is open loop control, and we're able to do it pretty well because there aren't any consecutive points in this M. So if you look at it in this plane here, we never reach steady state. We're always looking at the transients, and so we can actually push the limits of the system quite a bit and not run into problems down the line. So yeah, here's another look at it. So the idea is if we exceed a threshold value, we're no longer producing shark skin. So we'll give it an arbitrary value of 0.5 here. Anything above that, we're getting a nice clear letter. Anything below it, we're getting shark skin, and that's what we want. And so there isn't really any bleed between letters in our simulated piece. So yeah, here's a look at our open loop control. We've got a program I've written in C that's interfacing with the relay board, and we've got our 24-watt heater coils at each pin, as shown before. So on the screen on the right side here, I can actually demonstrate what's going on. Let's try to get this going here. So I got DOS running. We're high class going over here. Okay, so you see it's printed out UMass in SpaceFont, and it's been printed out a few times here. And so we got our relays clicking away over there, nice and happy, making space music, and I got some LEDs, and everything would link up to our extruder, and we get open loop M's, which look like that, and you can see it look kind of like the M in the simulation over there. So if you can't see it, it looks like there's the M. You can see Albrecht Dührer's M right there, nice and clean Roman serifs and everything. And yeah, so that works pretty well for the letters that never have to reach steady state. But if we're talking about something like an H, then we got some problems going open loop. So this section in here, we've actually, if we're pushing it real hard to get those transients, we're going to exceed the limitations of our insulation material, and we're going to get a bleed over. So you can see the bleed over in the H over there on the right-hand side. And that becomes more of a problem down the line once we get a whole series of letters. So if we had a bunch of H's in a row, then the consecutive letters would be more and more out of control because we don't have any feedback. So we got this nice Arduino system here. So here's a closed loop control algorithm. Basically, it's the same block diagram as before with our open loop boards, because I made everything modular. But we're looking at 3-channel PI control through the Arduino, which is kind of fun because the Arduino works really well for this. I'm only running at 40 hertz with the Arduino because we're kicking back serial data every 0.025 seconds. So I get an idea of what's really going on. And I was going to bring it in to show you, but it's kind of stuck to my extruder at the moment. So yeah, here's what we got is a picture of my board, and there's a cutaway of the heater pins that we're working with. So this is kind of my thermal test apparatus. So I can do some controller tuning without being actually next to the extruder and taking up lab space. So I've been driving Jim nuts with the pulse width modulation on that relays all day long. So in one slide, I'm going to tell you how we do iterative feedback tuning, which is gradient-based controller tuning. And kind of the basis of it is we've got our control loop. I don't know if any of you or all of you have taken controls, but so here's our control loop, right? And our G is our plant, which is the thermal response of our heater profile. And our CR and CY are, in this case, PI controllers. Now our CR has moved beyond our summation block because we're trying to get rid of a derivative kick. And then we're applying a tuning algorithm. So in this case, the point of the tuning algorithm is to find the lowest cost of a cost function. And in this case, so you can see a green line here, which represents the response of, I believe this is a fourth order system. And so the green line is what we want, the blue line is the actual response, and the cost would be the integral of that area between the two. And you could play games with both the system response and the control effort to get a best cost overall, depending on what you want to do. So we can apply that. I mean, we can also apply Ziegler-Nichols and basic tuning laws, but this is much more fun, really. I mean, come on, we got Simulink running. I already did system identification, so we do fun stuff. But here's our H with Teddy thermal control, and there isn't an H there, but you can see we're not getting any bleed over between the pins here. So everything is segregated to one side of that extrudate. And kind of the point of this graph here is to show you that we're not exceeding kind of tolerance values that we set on the plastic. So we don't want to burn it, for example. We can control exactly what we want and get a really, really fast response time on those H heater pins. So all in all, it's a pretty good system. It works reasonably well to print text. And the point of the project was proven in that we can accurately control the surface features of this extrudate. Now you ask, what's the point of controlling the surface features of plastic extrudate? Well, in our lab, Professor Rostein's primary research at the moment deals with drag reduction in microstructures on surfaces. And currently, the method they use to do that is a photolithography-based method, and it takes weeks, and it's a pain in the neck. So ideally, you could use something like this and tune it just right using my controlled feedback method here, and produce surface features of exactly the right amplitude and wavelength, not wavelength, but period that you want. So it's a pretty neat little step forward in that regard. Some final notes to conclude here. I got some interesting little things I learned along the way. Winding those coils is a real pain because they're all up to 2 inches long and 30 gauge wire, and they're all wrapped together. So I took a hint from your wire wrap tool, which is in the soldering room there, which some of you may or may not have even used, but made my own for winding heater coils. So if you ever need wind heater coils, I'm all set, good to go here. Step 2, when you're doing your thermal control, it's a lot easier to do with something with a smaller thermal mass when you're tuning stuff for the first time. So I made a breakout board for the LM35s. As it turns out, 30 seconds after I finished my breakout boards, I decided to open a random drawer in your part room, and it turns out you've got breakout boards for SO small outline transistors. And well, I learned a lot in the process. It was great. And step 3 here, this is the effect of cell phone noise on my temperature signal. And I couldn't figure out why on earth my controller would go haywire occasionally. Well, it turns out when you get a call and the thing's unshielded, the signal noise ratio goes crazy. Like this is getting a phone call from my mom over here, and that's the temperature actually recorded by the Arduino. So be very careful when you're doing your closed loop control and make sure everything's shielded. But if you have any questions, I'd be happy to answer them, and hopefully shed some light on this complicated, convoluted project. And I don't know, if you got questions, I'm happy to help you out.